This video is a quick tutorial in a couple of different calorimetry type questions. Have you ever heard of hot ice? If you haven't, I strongly suggest you do a YouTube search. When a supersaturated solution of sodium acetate crystallizes out, heat is released. So what is the molar enthalpy of solution? So what is the molar enthalpy of dissolving this? When 55.8 grams, we're going to need that piece of information, 55.8 grams of anhydrous sodium acetate. Anhydrous means without water, so it's just NaC2H3O2. There's no water crystallized into the structure. Remember we did hydrates last year. There's a period and then the number of water molecules that are attached. So anhydrous means no water. Sodium acetate is dissolved in 50 grams of water. The temperature of the water rose from 20 to 86 degrees. So a couple of things to note from this information. We know that we have 50 grams of water and the temperature of the water increased. So we know that the surroundings is the water. And that means the system is the anhydrous sodium acetate. So I write sodium acetate in a short form like that. AC means acetate. Okay, so the 55.8 grams is with the system. The 50 grams of the water is with the surroundings, as is the temperature change. So delta T is T final 86 minus 20 degrees Celsius. Okay. I should make that 50.0. All right, so where do you start? Normally, when you have calorimetry questions, you start with the surroundings. So Q equals MC delta T. We have 50 grams of water. Specific heat capacity is 4.19. And delta T is going to be 66.0 degrees Celsius. So your degrees Celsius cancels, your grams cancel, you're left with joules. So Q is going to be equal to 13408 joules, 13,408 joules. Now, because the change in energy of the universe is 0, we know that delta H is equal to negative Q. Now, the temperature of the surroundings increased. The temperature went up, which must mean that the system released energy. So, we can see that because we would have 13,408 joules released. So that's where the negative sign comes in. If you divide this by 1,000, you get kilojoules. All right. I'll make that a bit smaller. So now we have our enthalpy change. We can figure out our molar enthalpy. So we know moles is equal to mass divided by molar mass. 55.8 grams divided by 82.05 grams per mole gives us 0.68 0.8007 moles. Carry at least 4 significant digits here because you're using it again. It's an intermediate calculation. There's 3 sig figs in your mass, so because you're using this number again, you have to have at least 4 significant digits. So now we know the enthalpy change for the reaction is equal to the number of moles in the reaction times the molar enthalpy of solution. Rearrange that. Molar enthalpy of solution is equal to the change in energy for the reaction divided by the number of moles in the reaction. Just need to give us some more room. Okay. So negative 13.408 kilojoules divided by 0.68007 moles and negative 19.715 kilojoules per mole. Look at your initial data. Everything had 3 significant digits, so only 3 significant digits in our final answer. So the molar enthalpy of solution, the energy released when we dissolve 1 mole of anhydrous sodium acetate is 19.7 kilojoules per mole. That's quite a lot. So if you look up hot ice on YouTube, check out the guy that puts his hand in it as it crystallizes out. Alright, here's a calorimetry example where we've got 2 solutions that are mixed together. So we've got potassium hydroxide solution, and it's going to react with sulfuric acid to produce potassium sulfate and water. And when you balance this, there we go. Now, you will see these symbols in university, not so much in high school anymore, because we've changed the units to moles per liter, but this is 1.0 molar, so that's a big M for molar. But molar means, if you get a number and then a molar for a solution, it means its molarity. And that is the same thing as our units of concentration of moles per liter. So 1 molar solution has 1 mole per liter. 2 molar solution, 2 moles per liter. So the symbol for it is big M instead of writing MOL over L. Alright, so we have 200 milliliters of both solutions. The concentration is the same. The temperature increases 6.5 degrees Celsius. What's the molar enthalpy of neutralization? So it doesn't tell you in the question whether you should figure out the molar enthalpy of neutralization with reference to KOH or sulfuric acid. So what you need to do is look and see which one of these 2 is limiting. So using C is equal to N over V, the number of moles for each of our solutions is 1.0 moles per liter times 0.2 liters. So we have 0.2 of each reactant. So we need to figure out which one of our 2 reactants is limiting because they're not in a 1-to-1 ratio. We have 0.2 0.2, just going to pick KOH, 0.2 moles of KOH, and we need to figure out how much sulfuric acid is used. So we use our mole ratio from our balanced chemical equation. KOH is on the bottom because you want it to cancel. And the numbers that we use come from the coefficients in the balanced chemical equation. So we would need 0.1 moles of sulfuric acid for every 0.2 moles of KOH. And that's because we need half as much. If you look at the balanced chemical equation, 1 mole of sulfuric acid requires 2 moles of KOH. So we need half as much sulfuric acid as we have KOH. So that means sulfuric acid, 0.1 mole is going to get used up, and 0.1 mole is going to be left over in excess. So when we use the number of moles for the system in this chemical reaction, we are going to have the moles of KOH. Okay? All right, Q equals MC delta T. We have 400 milliliters total of solution because we mix them together in the calorimeter. Convert that to grams. You should always show this calculation. It's better to show it than just have random units switching up. So 400 grams times 4.19 joule gram degrees Celsius times temperature change was 6.5 degrees Celsius. So the surroundings increased in temperature because 6.5 was an increase. So we know the system was exothermic because the energy of the surroundings increased, which means it came from the system. Sorry, it came from the system. 1094. So 10,894 joules of energy went into the surroundings. So that means 10,894 joules were released from the system. Okay, resize that. Okay, so now, what is the molar enthalpy of neutralization? So we have the energy change for 0.2 moles of KOH used. So now we're going to figure out what the enthalpy change is if we have 1 mole. That's the definition of molar enthalpy, the energy change for 1 mole. So delta H is N delta H neutralization, molar enthalpy. Rearrange that. The molar enthalpy of neutralization is change in energy for this reaction divided by the number of moles in this reaction. So let's change that to kilojoules. So negative 10.894 kilojoules divided by 0.2 moles. And that gives us negative 54.47 kilojoules per mole. We're bound by our temperature and our concentration. There's only 2 sig figs, so negative 54 kilojoules per mole is the molar enthalpy of neutralization. So 1 mole would release 54 kilojoules. So because we have 1/5 of that, 1/5 of the heat was actually released. So about 10 or 11 kilojoules were released for 1/5 of the number of moles. Next example, last example actually. Carbon disulfide is burned in a calorimeter. What mass is burned if 1 kilograms of water increased by 15.5 degrees Celsius? So carbon disulfide here, this must be happening in a bomb calorimeter. Carbon disulfide is your system. It's getting burned, so it's a combustion reaction. So carbon disulfide is a system, but it says what mass. So we don't know how much was burned, but we do know the mass of the water and the temperature change of the water. So we're missing a key piece of information. This is working backwards. We know we have Q equals mc delta T. We know the mass, we know the specific heat capacity, we know the temperature change. So we can find Q. We have delta H is equal to N delta HX. So we're missing the mass, which would be involved in finding the number of moles. We can find delta H because we can find Q, but we don't have delta HX, and we can't solve this equation with two unknowns. But you just learned all about molar enthalpy and representing thermochemical reactions. And here we go over here, we have information. We know that if 1 mole of carbon disulfide is combusted, I don't know if that's a real word, is burned, then 16.90 kilojoules of energy are released. It's exothermic. So we actually do know our molar enthalpy. Our molar enthalpy is negative 1690 kilojoules divided by the coefficient in front of carbon disulfide. And you've got your molar enthalpy. Cool. Now we can start. So Q equals mc delta T. So we've got 1 kilogram, so that's 1,000 grams. I always do this for kilograms. I just take the number and multiply it by times 10 to the 3. I'm lazy. Well, I'm not lazy. I'm efficient. There's our specific heat capacity for water and 15.5 degrees Celsius. So, temperature of the surroundings went up, so the system was exothermic, so we should end up with a negative enthalpy change. So this is 64,945 joules of energy are absorbed by our surroundings, which means, always write this out, that delta H is equal to negative Q. That means delta H is negative 64.945 kilojoules. I took the joules, divided by 1,000 to change to kilojoules. And we are off to the races. Now we have delta H. We have delta HX. Delta H is N delta HX, so moles is equal to delta H divided by delta HX, but we also know that moles is equal to the mass divided by the molar mass. So we can solve for mass by moving, we times both sides by molar mass, We now have our mathematical expression. So, mass is going to be equal to negative 64.945 kilojoules divided by negative 1,690 kilojoules per mole times 76.15 grams per mole. Kilojoules are going to cancel, and our moles are going to cancel. I'm going to show you that up here. We've got 1 over mole times 1 over mole. When you divide by a fraction, it's like multiplying by the inverse. So this becomes mole times 1 over mole. So our moles cancel. And you will get 2.93 grams. So 2.93 grams of carbon disulfide are burned. Now, if you don't like doing this, last step, in one step, you'd rather do it in 2, by all means, do it in 2 steps. Delta H divided by delta HX. So this is going to be 64.945 divided by 1,690. Which equals 0.0384 moles. Now take, we know moles is equal to mass divided by molar mass. So mass is moles times molar mass. So 0.0384 moles times the molar mass is 76.15 grams per mole. And fancy that, you get the same answer of 2.93 grams. So there you go. 3 different types of calorimetry questions. Good luck.